The SMASH project at CMU is a hardware and software development effort that aims to provide search and rescue crews with advanced autonomy in support of finding survivors in disaster scenarios. We go about this by focusing on three core features, the first of which is human-in-the-loop autonomous search with a drone swarm controllable by a single human operator. The second core feature is network bridging that connects groups of rescuers, drone swarms, and sensors together, potentially over large distances. The third core feature is an open-source development platform that extends from hardware to software. This feature provides companies with accessible starting points to adapt our results to their needs. First, we build on the open APIs of inexpensive drones like the AR.Drone and 3D Robotics Arducopters. We also contribute to open-source projects like MADARA, a real-time middleware for distributed artificial intelligence, DroneRK, which is a toolkit for interfacing the AR.Drone with custom hardware like GPS and thermals, Android, which is an open interface between human operators and drones via the Android tablets and smartphones, and then finally SMASH CMU, which is a Google Code project that contains various AI implementations and glue code between the different open source projects. Understanding the scope of the SMASH project starts at the user interface. Here, one of our project members, Gene Cahill, is using our Android interface to center on the drones at Flagstaff Hill, one of the open areas next to CMU campus. Gene selects the drones available at Flagstaff and requests them to search a small area using a random area coverage algorithm.
When I get home, I shall write a book about this place.
After the drones receive their instructions, they calibrate their GPS, compasses, and other sensors, and they also coordinate with each other to establish their assigned altitudes in order to avoid collisions. Shortly after taking off and calibrating, the drones execute their search logic in MADARA. For the random area coverage, the drones select random locations at the edge of the search region and then move to those GPS locations. When a drone reaches a target location, it chooses a different target on a different edge of the search region. Developing for the AR.Drone is challenging for a number of reasons, not least of which is a flight controller that requires 80 to 95% of the CPU. If care is not taken to evaluate drone logic efficiently, the flight controller will be unable to adjust to its environment and the drone will destabilize, causing it to fall from the sky. To address this development challenge, we used MADARA, a reasoning engine specially designed for real-time systems, to execute distributed algorithms in a fraction of a second, providing us with the ability to execute even large, complex logics without impeding the flight controller. However, in order to use the engine for various types of machine learning and intuitive logics, we had to make significant improvements. Our contributions to MADARA included additional primitive types like strings, doubles, arrays, images, XML, and other payloads that could be transferred through the UDP, broadcast, and multicast transports. Additionally, we added filters for these types to allow for dynamic reduction of bandwidth usage and even the ability to slow down a publisher if necessary, which again helps us limit the risk of overwhelming the flight controller. We also ported the MADARA engine to Java to bring nanosecond execution time to AI operations on our Android devices. With the Java port in hand, our tablets and Java-powered applications can participate in the sensor swarm in real time. Another major feature of the SMASH project is completely decentralized control and a focus on algorithms and techniques that can be used in the real world. Most existing multi-UAV research has focused on indoor flight, with expensive motion capture systems and a central broadcasting server that controls the rest of the swarm. Though these systems are nice for precise, repeatable movements, especially indoors, they are unlikely to be useful for search and rescue crews who have to work outside over even small areas, especially areas with obstructions like buildings. So one of the more useful underlying properties of the project is a collaboration of the swarm to accomplish mission objectives, rather than being an extension of a centralized controller. For those interested in more information on SMASH or its follow-up project GAMS, which stands for Group Autonomy for Mobile Systems, we hope to release several more videos over the course of the next year. These include demonstrations of different area coverage algorithms, group formations centered around a moving tablet or specialized drone, network bridging between users and drones, and even some walkthroughs of developing for and interacting with MADARA drones and sensors. For additional information, presentations, and source code downloads, please visit our open source project pages listed below.